In the shadows of Cold War politics, two unlikely rivals, General Electric and Snecma, risked everything to create what would become the most widely produced jet engine in history, the CFM56. Experts call it the engine that saved modern airlines, but its birth was nearly strangled by diplomatic red tape, sabotage fears, and 5 years without a single commercial order. Why did the world almost bury the CFM56 before it ever flew, and how did it end up powering more aircraft than any engine on Earth? This is the insane truth behind aviation's most improbable success. Gerhard Neumann and René Ravoux found themselves in the heart of a diplomatic standoff that threatened to collapse their entire venture before a single engine was built. The US government, wary of sharing the advanced F-101 engine core, refused to grant an export license. National security concerns ran so deep that even the suggestion of sharing sensitive turbine technology with a foreign partner triggered alarm bells at the State Department and Department of Defense. In France, Ravoux faced his own government's skepticism, with officials concerned about becoming dependent on American technology and the risk of political backlash if the deal failed. Negotiations dragged on through 1972 and into early 1973, with both sides deploying their top engineers and diplomats. Locked room protocols became standard. In the French assembly plant, certain rooms could only be accessed by American personnel, and even Snecma's CEO was barred from seeing the high-pressure core. Every shipment of critical U.S. made components arrived under seal, tracked by serial number, and subject to inspection by export control officials. Congressional committees in Washington pored over every detail, debating whether the transfer would erode America's military edge or strengthen Western alliances. The deadlock broke only after urgent calls between Henry Kissinger's office and the Élysée Palace. In 1974, the joint venture received approval, but under strict conditions. GE would keep design authority and manufacture the core in Ohio. Snecma handled the fan and final assembly in France. The agreement limited technology sharing to a carefully defined interface, with regular audits and black box safeguards in place. For Neumann and Ravoux, the deal was a fragile victory, achieved not through trust, but through a web of legal, political, and physical barriers. The partnership could proceed, but every step would be watched, measured, and doubted. Doubts multiplied in the engineering offices of both continents. CFM's proposal to use composite fan blades, a material still unproven in commercial jet engines, sparked heated debate among airline technical teams. Early tests in the mid-1970s showed promise, but inspectors and certification authorities hesitated. Engineers worried about the long-term durability of composites, especially under the constant assault of bird strikes and runway debris. The memory of metal fatigue disasters from earlier decades lingered in their minds, fueling resistance to anything that might introduce new failure modes. Noise regulations were tightening as well. The CFM56's promise of quieter flight, thanks to its high bypass ratio and new acoustic linings, was met with skepticism by regulatory inspectors. Stage 3 noise rules, still on the horizon, threatened to ground entire fleets if new engines failed to deliver. Airlines feared investing in technology that might not meet evolving standards, leading to costly retrofits or stranded assets. Maintenance planners pored over test data, searching for evidence that composite blades could withstand thousands of cycles without hidden cracks or unpredictable wear. Some engineers inside the airlines lobbied for tried-and-true metal designs, citing the lack of real-world experience with composites. Others pointed out that the noise reduction claims had yet to be proven outside controlled test cells. Certification officials demanded more data before signing off on the engine. The technical controversy, layered on top of the political restrictions already in place, left many in the industry unconvinced that the CFM56 was a safe bet. For every bold claim from the joint venture, a chorus of skeptics demanded proof, slowing the path to market acceptance. 5 years after the ink dried on the joint venture, the CFM56 program teetered on the edge of extinction. Not a single airline had placed an order. The assembly lines in Ohio and Villaroche stood silent, workers waiting for instructions that never came. Every month, the joint venture's board, split evenly between GE and SNECMA executives, gathered to review the same bleak sales charts. The numbers told a story of mounting losses and evaporating hope. Internal memos tracked the burn rate. The cash reserves meant to last a decade had nearly vanished by 1979. Pressure mounted with every board meeting. Some directors, convinced the market had spoken, pushed for an immediate shutdown to stem the financial bleeding. Others argued for patience, but their voices grew quieter as the months dragged on. The technical teams, still refining composite blades and noise linings, faced the prospect of shelving years of work. Engineers who had crossed oceans for the project began packing their desks. The board issued a final ultimatum. Unless a major customer signed within 2 weeks, CFM International would be dissolved. This was not an idle threat. Contracts for suppliers were frozen. Recruitment stopped. GE and SNECMA prepared legal teams to unwind the partnership. The absence of orders had become more than a commercial failure. It was a public embarrassment for both companies and a warning to anyone who dared challenge the dominance of established engine makers. For the men and women who had pinned their careers on the CFM56, the clock was nearly out of time. Colonel Bob Miller sat in a Pentagon conference room in early 1979, holding the fate of CFM International in his hands. The U.S. Air Force needed to modernize its aging KC-135 tanker fleet, and the CFM56, unknown in military circles, was suddenly on the short list. Miller, known for his pragmatism, pushed through a deal that few in Washington had expected. The contract would see hundreds of KC-135s re-engined, promising a 25% cut in fuel burn and quieter operations, all while keeping the aircraft flying for decades longer. The decision sent shockwaves through the engine industry. For the first time, the CFM56 had a major customer, one that could not be ignored. Within weeks, the commercial sector responded. In March 1979, Delta Airlines, United Airlines, and Flying Tigers signed on to retrofit their DC-8 fleets with the CFM56, citing the same fuel savings and noise compliance that convinced the Air Force. Airline managers weighed the numbers. Lower operating costs, longer intervals between overhauls, and engines that could meet looming Stage 3 noise rules. The break-even point, once a distant hope, was suddenly in reach. The boardroom mood at CFM International shifted overnight. Where layoffs and shutdowns had been discussed, now production schedules and supply contracts took center stage. The KC-135 Varshar Award and the DC-8 orders together guaranteed enough volume to justify continued investment. For the engineers and managers who had spent years defending the project, the U.S. Air Force decision was more than a lifeline. It was validation. The CFM56, nearly abandoned, was now poised to change the economics of global aviation. Boeing's engineering teams, searching for a new engine to power the next generation of 737s, put the CF56 through a battery of tests. In 1981, after months of evaluation and behind-the-scenes negotiations, Boeing chose the CFM56 for its 737-300, making it the exclusive engine for the entire 737 Classic family. The decision sent a clear signal across the industry. CFM's engine had moved from outsider to standard bearer. Airbus, facing similar pressure to improve efficiency and meet new noise rules, selected the CFM56 for its A320 program. Within a few years, both major airframe makers had locked in the CFM56 as the default power plant for their most important narrow-body aircraft. Airline executives, watching the numbers from early adopters, saw maintenance costs and fuel burn drop. Orders accelerated, and the CFM56 began its climb to market dominance. Airline maintenance chiefs noticed something unusual in their fleet reports. CFM56 engines were staying on wing for for more than 30,000 hours between major overhauls, far longer than rival designs. This reliability translated into real savings, as airlines reported double-digit drops in direct maintenance costs and fewer unscheduled removals. Dispatch reliability rates soared, and aircraft powered by the CFM56 spent less time grounded for repairs. Fleet planners began to treat the engine as a long-term asset, shaping investment strategies around its proven performance. Yet, not everyone celebrated this dominance. Sustainability analysts and some industry critics warned that the engine's overwhelming market share discouraged risk-taking on cleaner, next-generation technologies. They argued that the CFM56's commercial success delayed the industry's move toward lower carbon propulsion. As CFM International developed the LEAP engine, they faced new pressure to balance reliability with innovation, knowing that the legacy of the CFM56 set both a high bar and a lingering debate. Over 33,000 CF56 engines have been delivered worldwide, with more than 1 billion flight hours logged since the program's launch in 1974. The joint venture between General Electric and Snecma began as a diplomatic gamble, nearly collapsing during a 5-year order drought until a U.S. Air Force contract in 1979 reversed its fortunes. Documents confirm that board minutes from this period show a program just weeks from shutdown. The engine's subsequent adoption by Boeing and Airbus transformed it into the backbone of commercial aviation, praised for its reliability and cost savings. Yet, some records about early export negotiations and proprietary technology remain classified, leaving gaps in the public history. Today, the CFM56's legacy continues through the LEAP engine, blending new materials and efficiency gains. The evidence is clear. The CFM56 did not just survive unprecedented obstacles, it set a benchmark that shaped global aviation and showed what international collaboration can achieve.